Okay, this is going to be the last of the lessons on the historical development of quantum mechanics. So today we're going to talk about the de Broglie wavelength, de Broglie waves. This thing right here is, is pronounced de Broglie. In my earlier videos, I may have pronounced this de Broglie or de Broglie, but apparently the correct pronunciation for that is de Broglie, de Broglie. Okay, so we're going to talk about de Broglie waves and the uncertainty principle in this lesson. Okay. So de Broglie's hypothesis was this. He made this in 1924. He said that if light has particle-like behavior, then maybe particle also behave like waves. Okay. So if you recall, we said that for light with wavelength lambda, the momentum is equal to h over lambda. So p is the momentum. Or you can say that the wavelength is h divided by the momentum of the photons that make up the light. Okay. Now, de Broglie suggested then that for electrons, for matter, for particles, electrons would also have a wave associated with it. So, for what we would call matter waves, the momentum, since the momentum is mass times the speed, de Broglie suggests that, well, maybe wavelength is going to be equal to h over the momentum, and momentum is mv, so the wavelength associated with a particle of mass m moving at speed v would be h over mv. Now, if you're dealing with very high speed particles approaching the speed of light, then you're going to have to use the relativistic mass. You're going to have to replace the mass by m naught here over the square root of 1 minus v squared over c squared. So you have to do the relativistic correction. M naught is the rest mass. Okay? So, consequence, consequences of wave-like behavior would be things like diffraction, just like light. Okay? And there's a very nice, very great video. I think this is the best one I've ever seen about wave-particle duality and introduction to quantum mechanics that I've seen from Yale, and this one's from Yale. So I'd like for you to look at that first. Okay, this one talks about the wave-like behavior of electrons, and so it also talks about the consequences of the wave-like behavior, which is the uncertainty principle. Okay. One thing before you watch this video is that to know is that he uses the symbol h bar, which we'll be using later on, and h bar is simply defined as h over 2 pi. Okay, so let's take a look at that. Also, there's another website. This Colorado Physics 2000 website has a nice animation of diffraction of electrons. Okay, so that's something you probably want to take a look as well. So let me pull up that website for you. Basically what you do is, okay, I already have it here. If you were to do a search on YouTube, just search for Yale Quantum Mechanics. Oops, oh, sorry, Yale Quantum Mechanics, and it will take you to this lecture number 19 for a physics class at Yale. Right, and this is the video. And if you click on show more down here, you can see at the 36-minute mark, that's when it starts talking about the wave-particle duality of matter. And one of the consequences of that wave-particle dual nature of matter and the wave-particle duality for light is the uncertainty principle. It talks about that starting at the 48-minute mark. Okay, so now this is a very good lecture, chalkboard lecture. If you want to start from the very beginning, he gives you a review of the wave nature of light, okay, the double slit experiment that showed that light is a wave, and then at the 9-minute mark, it starts talking about the particulate nature of light. We talked about that earlier in this class, and the experiments that demonstrated that light behaved like particles, the photoelectric effect. Compton scattering is an experiment, a phenomenon that demonstrates photon momentum. Okay, so if you have X-rays, an X-ray hitting an electron, an X-ray photon hitting an electron, you see the wavelength of the X-ray changes. The shift in the wavelength is due to a change in the momentum of the photon. All right, so let me go ahead and play this for you. I need to stop recording because I'm going to be putting this up on YouTube. So we'll pick up the recording of this lecture once we're done with this part of the lecture. Okay, so I'm going to let you watch from the 36-minute mark, wave-particle duality, on towards the end up to where it starts to talk about how wave-particle duality leads to the uncertainty principle. Okay, so let me pause this recording. Okay, so when is wave-like behavior observed? Yeah, I think so. So when the de Broglie wavelength, okay, lambda is comparable to the dimensions of the physical constraints. Okay, so h has, you see that h is a very small number. So in order for you, so when you want to calculate the wavelength, remember lambda is h over p. Okay, since h is a very small number, you would expect lambda to also typically be a small number. Okay, now quantum effects, wave-like behavior will be observed for your particle when this wavelength is comparable to the dimensions of the constraints. So like if you were to pass it through a slit, okay, what do you call this? The width of the slit must be comparable to lambda for you to be able to see significant interference pattern, wave-like behavior. Okay? So Davisson and Germer's experiment in 1927 showed electron diffraction, which is wave-like behavior, from nickel oxide crystals. So what they did is they fired an electron beam on a nickel oxide crystal, and so they have a movable detector here, and based on what they've observed, they were able to show that the electrons do in fact demonstrate diffraction pattern. The wavelength of the electrons used for this experiment is comparable to the typical distances between atoms in a crystal. So atoms are as close as possible in a solid, right? Typically that distance is around 1 to 2 angstroms. So with the electron beam that they used here, having a wavelength of about 1 to 5 angstroms, they were able to see diffraction pattern. Okay, so if you want more information on the Davisson-Germer experiment, you can go to Hyperphysics, the Hyperphysics website. Okay, so if you were to do Hyperphysics, just do a search, Davisson-Germer experiment. Somebody's already done that search apparently. Right there. So this gives you information about that particular experiment. Okay, so that was the experiment that confirmed de Broglie's idea that electrons do behave like waves. Okay, they have a wave-like characteristic. So so in other words, that confirms what we would call the wave-particle duality, a dual nature for the electron. Okay. All right. So let's do some simple calculations here. Let's calculate the momentum, the speed, and the kinetic energy of an electron that has a wavelength of 0.30 nanometers. So what equation do we need here? We're given lambda is 0.30 nanometers. How do we calculate P? P is h over lambda. Right? So h is 6.626 times 10 to the negative 34 joule seconds divided by lambda, which is 0.30 times 10 to the negative 9 meters. And that's how much? (6.626) times 10 to the negative 34 divided by 0.3 times 10 to the negative 9. So what you're getting? 2.2 times 10 to the negative 24? Okay. So 2.2 times 10 to the negative 24. What would be the unit for momentum? Momentum is mass times speed, so kilograms times meters per second, right? and see where that, how you come up with that unit. What's a joule? A joule is kilogram meter squared per second squared. So that's a joule multiplied by seconds over meter. So meters cancel, so that leaves you 1 meter on the numerator, and per second squared and second, that gives you per second. Okay. All right. So you got your momentum. How do you calculate the speed? You can use the Newtonian formula. So momentum is mass times speed. So solve for speed is P over M. So 2.2 times 10 to the negative 24 kilograms meters per second divided by, what's the mass of an electron? This is a good number easy number to remember, 911. 9.11 times 10 to the negative 31 kilograms. Okay, 911. So what would that be? I have 2.2 times 10 to the negative 24 divided by 9.11 times 10 to the negative 31 kilograms. That gives me, in exponential notation, 2.42 times 10 to the 6 meters per second. Okay. Do we need to do a relativistic correction here? What is that compared to the speed of light? Divide by 3 times 10 to the 8 meters per second. That's about 0.8%. No, 0.008. So yeah, it's about 0.8% of the speed of light. So that's kind of a low speed actually. So that's going to be a negligible correction. Because what was the correction factor you're going to have to do? 1 minus v squared over c squared, right? So if you make that correction, that's 1 minus 0.008 squared. So you're not going to be off by much. But if you are close to the speed of light, you may have to do this correction factor. Okay, so instead of m, what would you have to do? You're going to have to do m naught, right, which is the reduced mass, which is 9.11 times 10 to the negative 31 over 1 minus square root of 1 minus v squared over c.
You said the relativistic comparison, like you should divide this number that we got by the speed of light?
Yes.
And then
Well, you're going to have you're going to have a more complicated equation, because then you're going to say, all right, let's do this with the relativistic correction, okay? You're going to have to say now, you know your P, right? So you're going to say this is going to be equal to P, and this is going to be m naught over square root of 1 minus v squared over c squared. So that's equal to v, right? You'll have to solve for v. Yeah, so that's why I had you do that in MathCAD, because then it's going to be, you're going to have to do this just to solve for v. You have to solve for v first, and then you can plug in the numbers. Okay? In fact, let's see if we can do that in MathCAD. Is that the right formula, by the way? Let's see. Do I have it right in the numerator or the denominator? Yeah. Okay. All right. So if I were to do that in MathCAD, you're going to say that P over, what was it, m naught over square root of 1 minus v squared over c squared. The whole expression is equal to v, right? And now what I can do is solve for v, symbolic, variable, solve. And there's your expression for v. can say V equals that. Right, so that's going to be PC over square root of P squared plus M naught squared C squared. So let's continue. Let's try another example. Calculate the wavelength of a 0.2 kilogram ball moving at a speed of 1. I'm sorry. Huh? Oh, kinetic energy would be what? Kinetic energy would just be equal to 1/2 mv squared. Okay. Just plug in your mass and your speed. All right. So let's try this one. Calculate the wavelength of a 0.20 kilogram ball moving at a speed of 1 meter per second. First of all, okay, 0.2 kilograms, that's 200 grams, right? 1 meter per second. You've seen a ball that's about 200 kilograms moving at 1 meter per second, right? Do you expect to see wave-like behavior? Do you expect to see wave characteristics? No, and let's see why not. Lambda would be equal to h over p. H is what? 6.626 times 10 to the negative 34 joules seconds. Momentum is mass, which is 0.20 kilogram. And the speed is 1.0 meters per second. What would this number be? .626 times 10 to the negative 34 divided by 0.2. That gives you 3.3 times 10 to the negative 31. Okay. How small is that? Okay. Compare that to a nucleus. What's the nucleus of an atom? The width of a nucleus of an atom? About 10 to the negative 13 at the most, maybe, and then as small as 10 to the negative 14 meters. That is what? By a factor of how much? 31 minus 13, 10 to the 18. That's, okay, so that 10 to the 12 is a billion. 10 to the 9 is a billion, 10 to the 12 is a trillion, 10 to the 15 is quadrillion, 10 to the 18 is a quintillion. So that's a very, very small wavelength compared to even the nucleus of an atom. Okay, so you don't expect that to show quantum effects. You say, okay, you say that's a case where quantum effects are irrelevant. Okay, let's take a look at this one. Which of these two waves do you think represents a particle with a higher momentum? Assume the two particles have the same mass. Which particle would have a higher momentum? The one that has this wave right here, or the particle that's associated with this wave right here, the other one? Which? So let's call this A, and let's call this one B. B has higher momentum. Why? P is h over lambda, right? So which one has a larger lambda? A has a bigger lambda, right? That's your lambda for A, and lambda for B is this one. So you say lambda A is larger than lambda B. So bigger denominator means smaller momentum. So you say the momentum for particle A is going to be less than momentum for particle B. Actually, they don't even have to have the same mass. Okay. All right. So we say then that shorter wavelength is associated with higher momentum. We say momentum and wavelength are inversely proportional. Okay. All right. Now, Rutherford's alpha scattering experiment, if you recall from freshman chemistry, that's what led to the notion that the atom has a very tiny nucleus, and you've got those electrons going around that nucleus in a very, very large space compared to the actual space occupied by the nucleus, right? We said that at the very least, the electron cloud, the region, that mostly empty region around the nucleus has a diameter of at least 1,000 times bigger than the nucleus itself. So you're looking at a billion times bigger volume. 1,000 cubed is about a billion, 10 to the 9. A billion times bigger volume, bigger empty volume compared to that occupied by the nucleus. Now, there's a problem with that at the time. Okay, experimental evidence suggests that that is the way atoms are. You have a nucleus and electrons around the nucleus, and mostly empty space. But the problem with that, based on classical physics, is they know that if you have electrons going around in circles around a nucleus, those electrons are accelerating. And when you have a charged particle that's accelerating, okay, a particle that's accelerating will emit light, will produce light. So as an electron's accelerating around your nucleus, it's going to be producing light. So if it's producing light, it's losing energy. So if it's losing energy, what will happen to it? Eventually, it will crash into the nucleus. In fact, it will crash, classical predictions that it will crash into the nucleus so quickly that the atom as we know it could not possibly exist. So the resolution to that eventually was to say, okay, classical physics is wrong, okay? But there were earlier attempts to explain that. The Bohr model, okay, assumed that there must be some allowed orbits for electron for some reason. Okay, he didn't say he didn't try to say what the reason was, but he said there must be some orbits around the nucleus that is allowed for the electron. So that was the Bohr model. So that model of that so-called planetary model of an atom that you've seen in your early courses, that's the Bohr model. Okay. So Bohr basically suggested that there must be some specific orbits for the electron where for some reason it's allowed. Okay? And so Bohr's model was successfully used to explain, for example, the spectrum of the hydrogen atom. Based on these orbits, Bohr calculated what the energy of the electron would be, and then transitions from one allowed orbit to the other led to the correct prediction for the known spectrum of hydrogen. Okay, so that was one of the successes of the Bohr model. Unfortunately, the problem in the Bohr model is it works only for hydrogen, and it could not explain finer details. If you look at the spectrum of hydrogen at higher resolution, you cannot explain why those finer details are there. So, but Bohr was the first to propose the notion of quantization for the energies of the electron in an atom to explain it. Okay, so anyway, Bohr's theory about what the atom is, the planetary model, is now referred to as old quantum theory. Okay. Now, de Broglie was able to make a justification, sort of, for the Bohr model by proposing that the electron is a wave. Okay, and the idea in that case was sort of the justification for those stable orbits was to say that if you have one orbit that's allowed, okay, then it must be because the circumference of that orbit is a multiple of the wavelength of the electron. And so if you have a multiple of the wavelength of the electron, then you don't get destructive interference of the wave around that orbit. Whereas if it's not a multiple if the circumference is not a multiple of the wavelength, but you'll see, for example, let's say you start over here and you have a wave, okay? Then you may not end up there, so you would have all of this, and so you'd have destructive interference, essentially. In cases where you get destructive interference, you have a disallowed orbit. In cases where you have constructive interference, where the wavelength is where the circumference is a multiple of the wavelength, then you have a stable orbit. Of course, like I said, that model is no longer accepted because the Bohr model suggests a very precise, well-defined orbit, which is no longer acceptable, as you've seen. One of the consequences of the wave behavior, wave nature of the electron is the uncertainty principle. You cannot precisely determine both position and momentum of the electron simultaneously. Okay? So, in other words, this classical prediction that would predict how the electron would actually crash into the nucleus is simply wrong. It's not acceptable. That's not the way nature is. Okay, so it's the classical theory that failed to explain that. So we have to come up with a new theory to be able to explain. All right. So the uncertainty principle, okay, this is a consequence of the wave nature of the electron, as you've seen in that video. It's not possible to locate, okay, and know the momentum of an electron precisely at the same time. So the uncertainty in the position, let's say along the x-axis, times the uncertainty in the position along the y-axis is approximately equal to h. Okay. Now, when h being Planck's constant, when we're doing in modern quantum mechanics, if we precisely define exactly what an uncertainty is, if we define the uncertainty as a standard deviation, okay, so the standard deviation in the location of the electron and the standard deviation in the momentum, then we postulate that delta x times delta px is greater than or equal to h bar over 2. Okay, h bar is really nothing more than h over 2 pi. Okay, you see that h over 2 pi so frequently that we just invented a new symbol. Okay, so h bar, and you see that h with the bar on it across the h, that's h over 2 pi. Okay, so in that new lecture, starting at the 55-minute mark, we had that discussion about the wave, how the wave particle nature of photons and electrons led to the uncertainty principle. Okay? So what we're saying then is that the uncertainty principle implies that the predicted trajectory of the electron crashing into the nucleus is simply wrong. Okay? We need a new theory to actually explain the behavior of the world of the electron. Okay. Let's take a look at this one. Let's say the speed of a 0.5 gram bead is known to be within 1 millimeter per second. So that's delta V. Uncertainty in the speed is 1 millimeter per second. So that's 1 times 10 to the negative 3 meters per second. What's the uncertainty in the position? That would be 1. Delta x times delta px is approximately equal to h, right? So delta x would be approximately h over delta px. And what's p? P is mass times speed, right? So h over mass times delta v. Delta vx. Well, let's just say a particle is moving along the x-axis. So what is our answer here? H is 6.626 times 10 to the negative 34 joules second. Our mass of our bead is 0.15 grams. So that's 0.15 times 10 to the negative third kilograms. Okay. And the uncertainty in our speed is 1 millimeter per second. So 10 to the negative third meters per second. And that gives us how much?
Could you go back?
Sure. Okay. Yeah. Uncertainty in the speed is 10 to the negative third meters per second. Uncertainty principle says delta x times delta px is approximately equal to h. Okay. All right. So just plug in the numbers, plug and chug. What do we get? 6.626 times 10 to the negative 34 divided by 0.15 times 10 to the negative third divided by 10 to the negative third. Is that correct? 6.626 times 10 to the negative 34 divided by 0.15 times 10 to the negative third divided by 1 times 10 to the negative third. That's 4.4 times 10 to the negative 27. Okay, so here's your bead right here. Your position can be off by as much as 4.4 times 10 to the negative 27. Is that a big uncertainty? It's a very small uncertainty. So uncertainty principle, you'll find generally, because h is such a small number, okay, once you get into the realm of the macroscopic world, it tends to, again, just like the wavelength behavior, it tends to be irrelevant. But it becomes important in the world of the electron, in the world of the very small. Okay, so that's the important takeaway from this lesson. Okay, estimate the uncertainty in the momentum of an electron fired through a 100 picometer slit. Let's make that your homework. Okay, so you have a slit, 100 picometers in diameter. So this is going to be your delta x, right? And that's it for this lesson.